Yeah, yeah. If any questions come up, feel free to enter them in the chat. We will try to answer them as soon as we see them. But yeah, my name is Benny Benavidez. On the call with me, as I have Victor Bonachea. We'll be talking about SourcePack today. Essentially, SourcePack is a isolation switch that enables inverter-based solutions like energy storage systems for standby power applications. We've seen this evolution of the new energy landscape, the emergence of energy storage systems, particularly lithium-ion chemistries. And the big question is, how do we enable them for everyday use, and more importantly, how do we enable them for uh, emergency standby applications? So as we get into the presentation, I will introduce myself. As I mentioned, I'm Benny Benavidez. I've been with ASCO already going on 10 plus years. I started in the sales development program in Foreham Park, New Jersey, where our headquarters are located. I've held several roles through sales, marketing, strategy. My background is electrical engineering. My current focus right now resides in the new energy landscape, so the evolution of traditionally going from utility to generator, involving the newer distributed energy resources such as photovoltaic systems, energy storage systems, fuel cells, really having all those DERs play together nicely within a electrical design for microgrid resiliency, and of course with that collaborating with our larger Schneider entity, specifically on the wider Schneider portfolio, just seeing where our products align and driving solutions for our customers. Now I'll introduce my colleague Victor. Victor.
Thanks, Benny. So my name is Victor Bonachea. As Benny mentioned, I am the product strategy leader for ASCO Power Technologies, part of Schneider Electric now. I've been with ASCO going on actually just over 13 years now, with a background in electrical engineering and engineering management, especially focusing on power and control specifically. In that time in my career with ASCO, I started off as an application engineer, helping quote jobs, helping go through specs and all that before I kind of shifted more onto the R&D side, where I have focused on product development on anything from transfer switches to communication products to monitor systems to paralleling systems and across the board. During that time, I've been involved in a couple of external activities with IEEE, NFPA, UL, and creation of different codes and standards and updating them. And actually, most recently, with some of my work with local consulting engineers, I was awarded the Consulting and Specifying Engineer Magazine's 40 Under 40 for 2024 as one of the nominees for this year. So that's exciting. And I'm happy to be here today to be able to talk to you about SourcePack and these new isolation solutions that are going to become more critical into our evolving energy landscapes. Next slide, Betty. So we're going to cover a few things. We're going to start off going over some high-level market trends and what's driving this new energy landscape. If I can use a kind of a bit of a buzzword in all these microgrid conversations, as we go through what's changing and what's driving those changes in the market, we'll go a little bit more into the technology, and we'll start at the foundational level, talking about inverters and how maybe they're a little bit more different than AC sources like the generators where most of us are used to using every single day, and some of the different dynamics that causes and why the controls and the interconnection schemes have to be different than what you're used to with generators. We'll talk about some of the differences between transferring and isolation, as well as some of the standards around it and some of the solutions that exist today, and why the existing solutions out there today are not necessarily the best solutions out there, and why we're having to create new solutions to be more optimized for these applications. We'll go through some sequence of operations and talk through some of the recent product introductions that we've had in this space, really focused as a purpose-built solutions for these applications. And as mentioned earlier, we'll open it up for Q&A at the end. So the first thing worth talking about is the evolving energy landscape, as I mentioned. Traditionally, we have been seeing power systems for decades upon decades, which for the most part, there's always edge cases, but for the most part had a very top-down approach to them. They had sources, if you think about it, in almost like a pyramid shape, sources at the top, feeding power downstream toward loads at the bottom. Your sources were usually a utility, maybe generator backup, It was pretty much all AC until you got to your final loads. If anything required DC, it was usually converted to DC at the load itself. But all the power coming in was traditionally AC power. And it really flowed from top to bottom also. Not only were the sources at the top, the loads at the bottom, the power was always flowing top to bottom from the sources down to the loads. But what we're seeing now is that's changing significantly. The number of sources that are available, it's no longer just two sources. You can have many more sources, and they're not all just utilities and generators. You could have fuel cells, you could have solar, you could have battery systems, all those. And I call those sources, but some of those in many cases are not only sources. If you think of something like a battery energy storage system, sometimes a battery energy storage system is acting as a load when it's charging, if you're charging when energy is inexpensive, or sometimes it's a source when it's providing power out because energy costs are expensive and you're trying to subsidize those energy costs. And when it is a source, it's not necessarily always on the top of your power distribution system. It could be on the bottom where traditionally you've seen loads, and that kind of changes the dynamic because now that means that the energy can flow in both directions. The energy isn't just flowing from the top of your sources down to your loads. It could be flowing back up through your power distribution system to feed loads that are higher up in your distribution, or potentially even selling back to the utility if you have that kind of agreement with your local utility company. All of this kind of comes together and is causing different dynamics and the need for different types of controls and sequences and products in the systems that we didn't really need before because it was very well defined, the way the energy was flowing, the products that were in there. And that's what's really leading to the need for changes as to how we look at transferring and isolation and connecting other sources to the system. That's what we're going to go into more detail throughout this presentation. Now, what exactly is driving some of those changes? It's on the next slide. And Benny, I think you got that one.
Yeah, and also add here, it's really the evolution of what we call the prosumer. So now customers, instead of just getting an energy bill and just paying that, you have more autonomy to decide, how you consume energy and what you actually generate on site. If you're in a power purchase agreement, what you export back to the grid. So it really gives the commercial user and customer more autonomy over their power consumption. So what we're seeing here is market drivers for battery adoption, and we can start with ESGs, or known as environmental, societal, and governance goals. Most entities, businesses have these ESGs in place. Kaiser has them to be net zero by 2040 or 2050. Airports have them to be net zero by a certain target. Essentially, you can go about these three ways. You can reduce waste, and improve building efficiency, or you can incorporate renewables on site so you can generate or create energy from cleaner, renewable, sustainable sources. And that's the target. So apart from the economics, the dollars, these companies that have these initiatives in place to be net zero by a certain target, and accomplishing that one way is through battery adoption, capturing that excess PV, or to Victor's point, when utility rates are low, storing that and using that at a later time when demand rates are high or just peak demands into your system. Money everywhere. And what we mean by that is, the bipartisan agreement, like the IRA, a lot of money is made available today for federal, state, and local utilities to go after and collect some of this grant money to implement microgrids, improve the grid infrastructure. And a lot of that's funded through the federal government. So we're seeing a huge uptick in funds, particularly for school, military sites, federal funded businesses where a lot of this money is being invested. So that's a huge avenue and segment for microgrid and battery energy storage growth and resiliency, right? The need to have backup power available. One way to do that traditionally has been through a genset, but also through an energy storage system, you can enable resiliency. Now, to Victor's point, a lot of these energy storage systems they serve as loads, but if you design the system properly with adequate isolation, that energy storage system can provide backup power. We'll talk about that in the later slides. And then, of course, code requirement in the 2023 National Electric Code, that energy storage systems can be used as a standby source. But also, it's code required. State of California, they have it as a mandate for PV and battery installation on all new commercial residential builds. We just see this expansion of codes adopted throughout the nation as people get more in depth with energy storage systems and become more clever on how to use them for backup power applications. So the evolving market, we've reached a milestone here in California for energy storage. I think we've attained economies of scale where most manufacturers now have some energy storage product, and Schneider being one. Caterpillar, Generac, not to forget any others, but a lot of folks are entering the energy storage game, and a lot of that is due to the need to help out with renewables, to help expand also utility costs and help grow the grid. So with that, the main primary driver for battery adoption is energy cost optimization, or you could think of it as energy arbitrage, where you're charging your battery energy storage system when rates are low and discharges are expensive. Think about peak demand, right? You want to charge when utility rates are getting excess PV, and obviously discharge that to help smooth out those curves and help save on costs. Also driven by code, as you mentioned, it's referenced in the National Electric Code, Article 700.12G, where you can utilize microgrid systems as an emergency standby source. And then the need to, battery energy storage systems have several use cases. They can frequency regulation, help with peak demand. They're also a valuable backup power source. They do have a finite duration, but if you design them properly, you could utilize that energy storage system for a resiliency application.
Yeah, if you can go back one slide real quick, Benny, I want to talk a little bit more about the storing the excess solar for later use. One thing that a lot of people don't realize is if you think about a commercial facility, and let's say it's the weekend where you're closed and you're not running a lot of load, you might be generating excess solar, and a lot of people just default to thinking, let me sell it back to the utility company, right? And I can recognize the benefit that way. But the problem is, even when you're generating excess and you're selling it back, you're selling it for a fraction of the price that you're paying for your utility power. So if I were just to pick some numbers right now, because it's roughly 25% ratio, if you're buying energy at 20 cents a kilowatt hour, you're selling back maybe somewhere around 5 cents a kilowatt hour. That's usually what you see as far as that relationship. So you're actually burning basically 15 cents per kilowatt hour that you could have benefited from. So it's much better, as Benny said, to store that energy later for you to use it yourself rather than sell it back to the utility that I'm really not going to pay you a fair rate for it to some extent. So that's
Yeah,
one of the drivers behind energy cost.
Yeah, and that's kind of accepted, right? I mean, you're creating power through photovoltaic systems. I mean, the utility, that's power you're generating. You're essentially competing with the utility. So in essence, would they want to pay you a fair rate if they're selling it to you? Probably not, to incentivize you. But to Victor's point, it makes more sense if you can produce that power, consume it on site as needed to help reduce those energy costs.
Exactly. Thank you. So let's shift over a little bit now that we have some of the background why we're saying more microgrids, more battery energy storage, more solar, which often goes hand in hand with battery energy for the reason we just talked about. And let's take it to a little bit more technical and build that foundational understanding. And some of this goes pretty back to the basics, so bear with me. But you'll see how it builds up to the main story. Inverters overall are there to convert DC power to AC power. That's with rotating machines, that it's inherently AC power right off the bat. But when you have DC sources like solar panels, like batteries, maybe other things out there like fuel cells and things like that, most of our electrical systems today operate on AC in our distribution systems and facilities. So you need to get that over to AC to really feed it throughout your facility. So that's the job of the inverter. And what the DC source behind the inverter, it doesn't really matter. The inverter getting DC power, and it can be coming from any of those DC sources, the solars, the battery, whatever. Now, another term you'll hear us talk about a fair amount during this conversation and presentation are BESS systems, battery energy storage systems. Now, a battery energy storage system, it just really is a system, it's a product that's really combined of three key components. It's a set of batteries, of course, to store energy. It's a charge controller that is taking energy and using that to charge the batteries, be that power from solar, power from the utility, wherever it's coming from. It's using that to charge the batteries at the proper rate, at the proper current, so you don't burn the batteries or overcharge them or anything like that. And lastly is the inverter, as I just mentioned, which is actually being used to discharge the batteries and pull that DC voltage off of them, convert it to AC, and then feed it into your electrical system or AC loads. So when you think of BESS system, you might hear us switch back and forth between talking about inverters or BESS. A BESS, at the end of the day, is just batteries with an inverter and a charger. and it's packaged together as a complete solution at its most fundamental. So don't get hung up if you hear us go back and forth between those terms. Now, the interesting thing is a lot of inverters out there on the market, not all of them, but many of them, and many of them that you were seeing in these applications have two operating modes. There's grid tie mode, which goes by a couple different names. Some people may call it grid following also, or grid interactive. And that really means that the inverter is synchronizing its power output to another AC power source and providing the power out in parallel with it. Usually you can imagine it, or in common applications, that's the utility power source. Is tied into the inverter. The inverter is synchronizing to that utility source and providing power out in parallel with it to help subsidize your energy costs, for example. The other operating mode is grid forming mode or islanded mode, which is basically saying that there is no other source on the system. The primary source is your inverter itself, without synchronizing to any other anchor resource or anything like that. And it's providing power out onto a bus for the loads to consume without syncing up to anybody else. It's running independently, basically. And a lot of modern inverters have the ability to switch between these two operating modes. And that's where some of the complexity about using inverters for backup power come into play. One rule around the grid tie inverters is that if you're running in a grid tie mode and power does become unacceptable, be that under frequency, be that under voltage, or any other parameter like that, unbalance, the inverter must shut itself down. So it's a safety feature. It's actually defined and called out in UL 1741 and IEEE 1547, which are some of the standards around microgrids and inverters and things like that. And the reason it has to do this is for the safety of anybody who's working on the power lines. So say it is grid tied to utility and utility goes down and the inverter backfeeding the system, it could hurt someone who's trying to work on those lines, trying to repair whatever caused the outage. And it could also result in damage to the inverter itself. At that point, your grid, which was a source when the grid goes down, it essentially becomes a load at that point instead of a source. And your inverter, your best system, is going to try to feed that entire load that way, and it's going to overload your inverter and your best system, causing damage to it, probably causing breakers to trip or nuisance shutdowns or anything else. So you want to avoid that as well. And that causes some of the issues of, well, if I have to shut down the inverter when I'm operating grid tie mode, which I want to do most of the time to recognize my energy cost optimization, then how are you telling me that we can use it for backup power as well? That's what this whole presentation kind of leads into. Next slide, please.
Yeah, I'll just add also, when we're talking about battery energy storage systems, these are commercial offerings. So behind the meter, it can even be front of the meter, but these battery energy storage systems are all in one. What we mean by that is they include the inverters, they include the batteries, the racks, the power control system, the inverters, the HVAC systems. They're compartmentalized, tested to UL 9540, 9548 for thermal propagation. So their commercial BESS is a little different than the residential. So I just want to note that when you do specify a BESS, you're getting an all-in-one that's designed for outdoor installation.
Yep. Cool. So as we continue to talk about that need for isolation and inverter shutting down and things like that, I bet that some of the people on the call, at least more than 10, let's say more than half probably, at some point have had a conversation. Let's not even talk about commercial or industrial. Let's talk about residential, with a family member or a friend or somebody who's thinking about putting solar on their house. And that person probably said something along the lines of, well, I want to get solar in my house to help me reduce my energy costs. And at least if there's a blackout, then I have backup power. That's a myth. That's false for the reasons we just went over. If your inverter is operating grid tie and there is a blackout, it has to shut down when it detects that blackout, that brownout. Whenever it detects the utility source it's synced to is unacceptable to prevent the backfeeding, to protect line workers, things like that. If you look at the left-hand side here, you see an example of a system without isolation that does have an inverter source on it, and you'll get energy cost optimization out of it when it's working grid tie. But if utility fails and that inverter turned back on, it would backfeed back up to the utility, as you see. And for that reason, it can't, and that's why that standard exists and that requirement. It cannot be used in that case for standby power applications without that proper isolation. However, on the right-hand side, the truth is, yes, you can use it for backup power if you have an inverter that supports grid forming mode, but you just need to also have the proper isolation in your electrical system. And now you see here, we've introduced a disconnect, an isolation point, an interconnect point. You'll hear a lot of those terms used interchangeably. That when utility fails, that interconnect point here labeled as source packs can open up, basically creating an island, a smaller separate electrical subsystem, a microgrid, if I'm using the buzzword, that when the utility fails, it breaks off that portion of the electrical system in your facility, and that portion still retains your essential loads that you want to back up, as well as your inverter. And now that inverter is able to come back online and provide power in a grid forming mode to keep those essential loads online. So power is good. That isolation point is closed and everything's operating grid tie. Power goes bad. That isolation point opens. Inverter provides power and grid forming, and your essential loads are back online. One other clarification point I just want to make here. I've given this versions of this presentation a few times. There are utility and code requirements for disconnects and isolation points on the inverter for lockout, tagout reasons, for serviceability reasons. That is different than the isolation and the interconnect into the electrical system as shown here. That disconnect would be something directly at the output of the inverter so that you can basically take it offline from your entire system and do work on it and ensure that it's disconnected. You can't have that be the same as one of these isolation points, because if you take it off at that point, there's no way for power to get from there to those essential loads. So the isolation for serviceability and for disconnect reasons at the inverter is separate than the isolation or internet connect point to the utility, where you might island part of your overall facility's electrical infrastructure, which includes your inverter as well as your essential load. So those are just two separate things that are very easy to kind of mix together sometimes, but they're in fact two different use cases. So let's just keep that in mind.
Good clarification there, Victor. Okay, so isolation methods today, servicing customers, these, and we've seen a couple single line diagrams where they're misapplying automatic transfer switches. They're using ATSs to create isolation where they're only connected to one power source, leaving the second power source just idle with no power connections. Manual interlock schemes, see manual transfer switches or per key interlock schemes to create this isolation. Self-assembled solutions where we've seen contactors, relays installed, basically assembling these solutions on site, putting a lot of stress on the contractor. And the downsides of these, uncrewed, isolation methods, it's gonna be labor intensive. Especially if it's the first time, someone's installing one of these microgrid systems or interacting with the energy storage system. You want to make sure you get those installation requirements hashed out before the rest of the job site. Improper application. Again, if you're using an automatic transfer switch for isolation, the UL 1008 listing is specifically to transfer load to another power source, not for isolating. That's not what the UL listing was approved for. So you could see some unforeseen applications if you decide to go that route. Lack of standardization across the industry. So energy storage systems, although we're relatively familiar with the technology, it's still new. I think probably under a decade before we had, this commercial availability of an energy storage system. So there's a lack of standardization. The codes are just getting up to date with, utilizing energy storage system as an emergency standby power source, and also difficulty to get approved by ASJ. And ultimately, what we talk about today is, we work with the consultants, the vendors, but ultimately, you need to work closely with your ASJ to get this approved to make sure that they're on board with the solution and get everyone on the same page. And with this, there's an equipment approval listing within the National Electric Code that, interconnection and interactive equipment must be connected to or operated in parallel with the primary production sources and must be able to disconnect and bring on alternative power sources to the system. So there needs to be a product that's, tested to safely isolate from the primary source and connect to other alternate sources, which we accomplish. We reference it as, an automatic interconnection switch. The National Electric Code references it as a micro interconnection device. The two are interchangeable, but that is the approved product that we're looking for today. It's the micro interconnection device.
Yeah, especially as the National Electric Code now is allowing microgrids and battery energy storage systems to be used to feed power to emergency standby systems. One of the code excerpts on the previous slide you'd see mentions that one of the requirements is when you're using it for an emergency standby application, it must be listed for that application. So a lot of the options here are either products that are not listed for that because it's a different type of product, such as an ATS, which doesn't do that kind of sequence of operation, or it's a self-assembled solution or a custom solution done by an integrator that probably doesn't have a standardized UL listing, which can make it very difficult to pass any sort of inspection or anything like that, rather than a purpose-built device for that application and listed for that application as well. So, next slide.
Yeah, so we look at transfer versus isolation. I like to show this slide because it distinguishes the two. We look at an automatic transfer switch. Transfer switches are selected between utility or generator. It's never both. And what we mean by that is the generator is almost never in parallel with the utility, unless there's a soft load transfer or CHP unit. But primarily with ATS, it detects utility. There's an acceptable source, voltage, and frequency. Once we detect that there's been a change or it's a dropout, that ATS will send a start signal to the generator. Keep in mind source one is lost power, there's no power, and then send a start signal to the generator. Generator comes online, and then that generator power on source 2, the ATS, energizes the contactor within the switch to initiate transfer. That's the key distinguisher: transferring load. Whereas an isolation switch, is utility and battery storage. Remember, the two are both connected. Batteries act as a load. They can also serve as a power source. So during normal operation, your battery energy storage system is acting as a load, or projecting current into your system to offset utility costs. And the key distinguishing point here with isolation switch is that it detects the utility outage, much like a transfer switch. It has a controller that monitors voltage and frequency. Once that voltage and frequency drop out or hit that utility, it will isolate, so it'll open that breaker, send the contact signal or start signal to the battery energy storage system, the power control systems, inverter systems, to change state from a grid tied to a grid forming mode, where at that point the energy storage system is now safely segmented. You segmented your essential loads, and you're providing backup power to those essential loads only, isolating the rest of your facility. So in the event that utility does return, you don't have to worry about a backfeed. You're safely isolated, and then the source isolation switch can detect that utility's been returned, signal the battery inverters to shut down again, operate again, grid type operation.
So if you, Benny, can you go back to that one? If you look at the diagram on the left, the transfer switch, if you imagine the places you can place an inverter on here and why the transfer switch won't work, and this will help when we go through a one line in a few slides. If you replace the generator here with an inverter, well, that's not great, right? Because 90% of the time you do want to be connected to utility, in which case your inverter and your BESS system completely out of the picture. And well, part of the big value prop behind an inverter is you want to do energy cost optimization, and you won't be able to backsell because the inverter basically disconnected from everything else on the system. So well, you can't put it on the generator side of an ATS. Well, if you put it on the load side of the ATS, then all of a sudden power fails. You want to run on the inverter. Well, the inverter is still tied in with the utility at that point, and because you're still connected to normal, and without an emergency source, an ATS can't disconnect from the utility source. So you're stuck there, and so that's no good. And then you put it on the utility source itself. Well, that's just not providing you any isolation, because the moment you go to emergency, if you go to emergency, if there's another source to allow you to transfer that switch, you can't get power to those loads at that point because the inverter is tied in with the utility. So an ATS really doesn't fit the bill, and that'll be clear in an upcoming one line. Meanwhile, to Benny's point on the isolation side, isolation switch, you can run parallel with both of them until you have an issue with your main power source, and then it isolates, and you're still got your inverter connected to your loads. So I just wanted to clarify that point so that you can follow the one line.
Yeah, good points, Victor. So isolation considerations for emergency systems. I think the primary one we're thinking about safety is to prevent any backfeed to the utility system. To Victor's point, when we lose utility power or that primary power source, the inverters inherently shut down. The reason they shut down is in the event that you can't create isolation, you're preventing any backfeed up to the workers that are helping fix or bring back utility power. Another point of consideration for isolation systems is you can provide power to your central loads. So if you look at our block diagrams, I mean, with an automatic interconnection switch, you're isolating a portion of your electrical facility for backup power to your energy storage system. Whereas conventionally, you would provide power to your entire system. And as you know, battery energy storage systems have a finite duration of power. So if you're going to utilize it for a backup power source, you got to make sure you section off the essential loads so they can get power. Automatic reconnecting and eliminate the process of manual intervention, and you can safely automatically disconnect and reconnect to that primary power source once it's returned. And of course, we have the code requirements, the latest revision of the National Electric Code 2023, where energy storage systems can be utilized for emergency power applications and be used within system operation to be utilized as a primary or alternate power source.
So over here is actually a one-line diagram that was provided to me by Benny, actually, from a real-life example of a project where we were pulled into, where they were trying to design a system where they had isolation being provided by an ATS for an inverter. And it's a great example of what we talked about before, people misapplying ATSs for this application where you really need a purpose-built product. So let's walk through it real quick. It's kind of reverse. Usually think about the sources on top and the loads on the bottom, like we talked about. In this case, it's a little bit backwards, but bear with me. On the bottom left corner, you'll see some transformers, and that's kind of the utility feed coming into the facility that feeds all those boards at the bottom along the right with some of the loads on the facility. But then we see kind of in the middle, there's a branch that's feeding up to that transfer switch within the red box. Feeding up through that transfer switch to the red box, you go a little bit higher up. What's actually listed as the normal side of the ATS. It's actually feeding the utility in from the load side up to the normal side. Is feeding another distribution board with elevator loads, and one of the breakers on that board is feeding downstream, where it's actually connected to an inverter. Now that's the inverter that they want to be able to operate in grid time mode most of the time, and helping feed power to the rest of the system and optimize costs with normal operation when utilities could. But the intention here was that when power fails, the utility power fails, that ATS would provide the isolation so that the elevator board and that inverter are disconnected from the rest of the facility's distribution system, which would then allow that inverter to turn back online in grid forming mode and provide power to the elevator distribution board right there. Unfortunately, it's not going to work. Again, because ATSs are not designed for this application. And it's not just a question of how are they listed or terminology or anything like that. They functionally will not work. The reason being that most ATSs on the market by by all manufacturers pretty much require power from the source. From a power source to be able to transfer. They energize some sort of mechanism, be it a solenoid or a motor, to actuate physically the contacts in the switch. So in this sequence, if utility power fails, and immediately upon utility power failing, the inverter is shut off because they're still technically tied to utility, there's no longer any power on this system for that transfer switch to flip its contacts and island that elevator distribution board and that inverter, which would allow you to turn on that inverter. When it's a generator application, that's not a problem because on that emergency side of the switch, the emergency would start up, the generator would start, and then we would pull power from the emergency bus to energize those solenoids or motors to drive the switch. But in this case, all power sources are offline, and the only one that could potentially turn back online, which is the inverter, can't because it's still tied to the utility. So there's no way to actuate that switch in this case to provide any sort of isolation for those loads. You're kind of just stuck in the connected position permanently. Which is a great example of, again, people misapplying ATSs into applications where an isolation device, an isolation switch, interconnect switch, is really the correct solution to get the functionality that they are looking for. And I believe I saw someone in the chat ask before, so it acts like a transfer switch, referring to the isolation switch. Well, I think this kind of clarifies the difference between a transfer switch and as we're going to continue to talk about isolation switches and their intended purpose and how they work. Next slide, please. Now, the thing is the concept of isolation switches and interconnection switches are relatively new concepts out there as microgrids are evolving and the need for these types of isolation devices are forming out there. And there was actually no standard out there. As we mentioned, if you're going to use them for emergency standby, they have to be listed. Well, there was no existing standard, and because there was no existing standard, it was difficult to get any sort of UL approval on them if you don't have a standard to list against. So, so UL, in partnership with Schneider, actually developed a new standard known as UL 3008, which is for automatic interconnection switches, as we call it. Now, the process to creating a new standard, let me go over that very briefly to provide the context, is that any company can partner with UL to develop a new outline for a standard based on them being able to convince UL that there's a market need for it. So a company can partner with UL, come up with a draft of that standard between a subject matter expertise from that company together with UL's experts, and publish that basically as what they call an outline of investigation, which is a fancy way to say a provisional standard. A provisional standard is something that can be listed against and can be designed against and used just like a regular standard. But unless the industry buys into it in the near future, it eventually just kind of goes by the wayside. So once a product becomes a provisional, once a standard gets published as a provisional, as an outline, the next step is that you need to expand it to the industry to provide commentary and editorialize it and vote it in. So at that point, one company starts it with UL, but then once it gets published, all other subject matter experts in the industry can start commenting and providing feedback on it. Other manufacturers, be them competitors or not, other subject matter experts, consulting engineers, end users, anybody who has any sort of expertise on it. And once they all reach a consensus, then that group has to come together basically in committee and vote it in to have it be published as a full standard. So the UL 3008 standard is a provisional standard and outline that was created between Schneider and UL that is currently in the process of moving towards a full standard with the rest of the industry around interconnect switching. And the idea behind it is that if you have transfer switches with generators for backup power, that an interconnect device which basically enables an inverter to provide backup power, should not be any less robust or any less reliable than what we expect out of a transfer switch and generator. So obviously you can see the inspiration between the two, UL 1008, UL 3008, they're parallels there. And a lot of the testing standards around the two do mirror each other. But there are advances. The standard covers things like short circuit performance, endurance performance, overload performance, temperature rise, all those things. But then are just like transfer switch UL 1008. But then it goes as kind of a step further, brings in other pieces that are unique to this application, such as support for bidirectional flow. Transfer switches are usually tested and qualified to power flowing from the sources to the loads, as we've talked about. But in this case, since power can flow in both directions, every single test essentially that was done to qualify it has to happen twice, once with the power flowing downstream and again with the power flowing upstream. So the first step is creating this standard that such a product can start driving some industry standardization, since it is kind of the Wild West out there around these kinds of solutions, and drive some level of guarantee to customers and users of the reliability and robustness of such products.
Yeah, and then for those that are interested in learning more about the UL 2008 outline investigation, you can log on to UL webpage. Create an account, is free, and the outline investigation is available for review for anyone that are interested in learning more about the UL listing and what it entails. So, source isolation switches. So the product you see here in the top right, this is source pack. It has a motorized breaker. On top of that breaker, it has a controller, and this device helps isolate safely from the utility to enable greener, more sustainable inverter-based sources to provide backup power. Now, this whole focus here, we're talking about enabling battery resiliency. That doesn't, overlook the fact that we're talking about reliability in a different aspect. And if you're considering designing a microgrid system or incorporating energy storage, it's very important to also consider reliability, right? Again, these energy storage systems are, capable of providing backup power for 2 to 6 hours even. And if you're looking for longer duration, a generator is still a very pivotal piece to that microgrid system. If you're looking for prolonged alternate power sources. When it comes to SourcePack and enabling energy storage systems, it's a perfect product that's designed specifically for this application, tested, and it's easy for installation. We just set up a research and development lab in one of our facilities in North Carolina where we can showcase and virtually test this isolation device with the energy storage system. Really, it's one of a kind. The first interconnected isolation switch designed to UL 3008. So new testing criteria to showcase its robustness and rigor in the design criteria. And if you're considering, you incorporate an energy storage system within your facility with PV, you would also want to maximize on the backup power resiliency, and SourcePack enables you to safely isolate and at a very basic level have a microgrid controller to talk to the inverter system. Whereas some other solutions, they provide an overspecified product where you're electrically modifying each breaker, adding a PLC, really adding costs and more simple transactional business. If you're looking to create isolation to enable that battery resiliency, the source isolation switch is one approach to achieve that. And we'll use the analogy: what an ATS is to a generator, SourcePack is to a battery storage system / inverter system. And that's the way you can probably look at it in order to connect the dots.
Yeah, so let's go through a sequence of operation for a isolation device or SourcePack. Usually what you're going to have is you're going to have your utility system online most of the time, 99.999% of the time, your nines of reliability. And that's going to be feeding power to what, if you look at this one line here where the standard loads are connected, you can think of that as your main board coming into a building. There's going to be a service entrance on it, some feeder breakers to some non-backed up loads, but there's going to be one feeder breaker coming off of that load down to through a SourcePack, feeding another board, which you can consider almost like your emergency sub panel if you're familiar with the way we architect some of these smaller generator systems. On that emergency sub panel that's being fed through SourcePack, you're also going to have a breaker, and that's where your inverter or your solar is going to be connecting into the system as well. And that allows your inverter system to be able to charge off of the utility if it wants to, if it's a BESS system and you're using utility power to charge it. Or if you're playing with the energy pricing through your tariffs or through solar, allows you to feed power back up, feed the loads on that emergency sub panel, or even push that power further upstream to the loads on your main panel, or even back to the utility if you have a back sell agreement with the utility. And that breaker is going to be closed most of the time because that inverter can be in grid time mode. Now, when utility power fails, SourcePack or an isolation device is going to detect that because it has onboard metering that is monitoring the utility at all times. When it detects that power failure, it's going to go ahead and isolate the onboard breaker in the SourcePack and the isolation device. That then islands your essential loads on that emergency sub panel and your inverter together, islands it away from your utility and your non-critical loads. It'll then go ahead and send a signal from SourcePack, from the isolation device over to the inverter, dry contact, telling the inverter and letting it know, hey, you're isolated. It's safe for you to switch from grid time mode, where you have to be shut down, to grid forming mode, which means you can come back online and you're essentially the only power source on that bus at that point in time. And you're going to operate in this mode indefinitely, or not indefinitely, until you exhaust the charge on your batteries, or until you run out of solar power for whatever reason. But you're going to run on that essentially until either you exhaust your energy sources or until utility power goes ahead and returns. Next slide. When the utility power returns, the metering onboard the inverter, onboard SourcePack, is metering both sides of the interconnect of the isolation device. So it'll see that utility power came back, and I'll say, hey, after some time delays that are all user configurable, it'll signal the inverter, hey, go back to grid time mode. So the inverter will switch back over, but it doesn't have a utility source to sync to because that breaker is still open. Once the isolation switch confirms that the inverter has shut down, it'll go ahead and reclose that breaker, re-energizing that sub panel or that bus with utility power, which gets your emergency loads back online, and your inverter will see that power as well again and sync back up to it and start providing power out in parallel. So it's almost like if you think about it from the ATS world, because we are drawing a lot of parallels, it's almost like an open transition transfer between the two as you transfer to and from the inverter being grid forming mode. But in this case, it's isolation and just changing modes rather than starting a generator.
So if we look at some of the core architectures here, so what Victor talked about, there is on the left the battery only, where you have some utility downstream, so not essential. All that utility for way downstream, you have source pack that is segmenting those essential loads. So in the event that you lose power, you can provide power to those essential loads that require, backup power through the energy storage system. That's the most simplest design. There are also applications where battery and generator coexist. As I mentioned earlier, these battery and storage systems have a finite duration of the power. So depending, if the outage prolongs longer than 6 hours, you have some life safety equipment. It's very important to at least have that on generator or backup power. So here in that middle diagram there, we have an ATS that's connected to a generator feeding essential loads. And then we also have the source pack device on the right feeding essential loads, which again, when we're working with a consultant or a contractor and user on the design, we want to understand, what is the load prioritization, which loads have criticality, which ones must be on at all times, and which ones after a prolonged outage can accept the power outage for X amount of time before utilities restore. And then on the far right, we have a battery first scenario where in the event that the battery energy storage system is upstream, so in the event that you do lose power, instead of immediately sending a star signal to the generator provide power to the essential loads, you run on a battery first scenario where you'll have the battery energy storage system act as the anchor or the emergency anchor resource, providing power, basically inhibiting transfer to the ATS to stay on normal. They'll provide power, and then once that battery energy storage system, let's say, reaches 4 hours emergency power and it's at a low state of charge, that ATS intuitively will detect that, hey, source one is no longer available. Let's start the generator for those prolonged outages. So different scenarios on how you can go about designing, energy storage for resiliency, whether it's battery or generator, different approaches we could take to make a solution that's encompassing a battery or battery and generator. And with that, this leads to source pack. So a lot of the automatic interconnection switch, the UL 2008 listing, all that is based on our latest product, source pack, and the National Electric Code to be referenced as a microgrid interconnection device. And this is the industry's first purpose-built solution for automatic isolation and reconnection to utility to enable inverter-based sources to provide standby power. We talk about lithium-ion chemistries, but there's different types of energy storage systems out there that they want to be utilized for energy storage. We're compatible with them. Source pack is only an isolation switch with a very basic level microgrid controller to talk to the energy storage systems inverters. So really vendor agnostic, and we're going to streamline this product out in the industry. For our initial launch, the product is available at 600 amps at 480 volt. That's the most common we see out in the industry, and you'll see within the energy storage systems, they'll have an output transformer to step up the voltage to 480, 60 hertz, 3 poles, solid neutral. As you know, most energy storage systems, if you come across them, are intended for outdoor installation. So source pack is designed to come with the NEMA 3R enclosure as a standard. That's installed, outdoors. You'll run some, contact wires to the energy storage system. So really there to simplify design and to match the energy storage system. And we do that through C-form contacts. Well, we have some dimensions and data there, but if anyone has, questions about the product or has a project in mind that, requires isolation or wants further clarification, you can always reach out to us or drop a question here in the chat. If you scan that QR code, we have our data sheets, white papers, wiring diagrams, and outline drawings available on our webpage. But of course, if you do need further information, you can always reach out to me. I'm the commercial lead. So for ASCO, I cover the microgrid solutions, not just for the West region, but for the whole country, supporting all sales offices and leading the commercial launch for SourcePack. So again, I thank everyone for their time today. If there's any questions in the chat, I'm happy to answer them with the remaining time we have left, but I appreciate everyone's time today.
Thank you, Benny. And we do have a few questions in the chat if you all can take a peek. And I went ahead and added them from the Q&A to the chat.
Sure thing. But do you want to take a look at them?
Yeah, I'm looking at some right now. Give me 1 second. All right, so I'm just going to try to start from the bottom up. Please verify that the essential loads can be energized within 10-second requirements. Yes, I want to say yes with an asterisk on that. So the isolation function itself happens extremely quickly. It's approximately 1 second or less. The final speed of your entire system being back online with your inverter in good forming mode is going to be a function of the speed of your isolation and how long it takes your inverter to come back online, which is unique to your inverter. Just like it's with a generator system, it's about how quickly can you transfer, how quickly can the generator come up and for you to transfer. So from all our investigation and research, with an average inverter that comes up quickly, and the isolation where will within the 10 seconds. However, at the end of the day, if you're using an inverter that's very slow to respond or something like that, that could be problematic. So yes, very well within the realm of 10 seconds, but it depends on the design of your specific system and the inverter that you select to use. I see a couple questions around I think the same topic around having the utility requirements, many utilities requiring a protective relay. And one of the questions someone's calling out SEL 751 and others, and asking if that's included in here. And the answer is no, that's not built into this product because usually this product is not intended to be traditionally at your service entrance. It's intended to be further down in your distribution. And if you're thinking about things like reverse power or things like that, that's actually something you want in these applications. If you're using like a sub panel application, like we said, for your emergency, when you're working in emergency mode, in grid forming mode, you want that panel to be isolated and no power to be backflowing because the breaker is going to be open, right? But when you're in grid tie mode, if you are producing excess capacity, you want your full facility, not only your backed up emergency loads to have access to the power, you also want your non-backed up loads further upstream to have access to it. So your utility protection would have to be on the utility incoming feed, basically at the service entrance would be the optimal location for that. And since this is not usually going to be used in that application, it's not built into this product.
Yeah.
The UL3, go ahead.
Yeah, the UL 3008 listing. It's
I was about to go into that. Yep. Go ahead.
The service entrance radius, so for that point, it removes us from the point of interconnection with utility requirements. That's intended to be downstream, really, of the utility main switchboard. And for that reason, it's an automatic interconnection switch, and we kind of bypass the interconnection requirement with the utility.
As the UL 3008 standard evolves and does allow for service entrance applications for these interconnect devices, I definitely expect that to happen in time. And then at that point, for those type of protective functions to be in the scope of these offers at that point.
Yeah, when as it evolves, I mean, we could probably see if it does at some point become service entrance rated, incorporate these relays. But as of today, still very much as infancy as a launch. So get feedback from the field and see if we need to alter it to make it really a point of interconnection or service entrance rating. But today, it's not intended for that.
Benny, maybe could you address the one about are there any environmental or energy grants from California or a federal government that this product may be eligible for?
As far as grants, I mean, most of it was like a made in America, right? That's probably one. I'm sure there's a couple of incentives within California that can be utilized, just California across the nation to get some IRA dollars. If there is a project in mind, I mean, I could probably put you more closely with our accountants that look at that, primarily those folks that do energy as a service and really decide on your local utility, what incentives are available, what grants they're pursuing, and then where to procure equipment so you can maximize on some of the incentives. But if you guys drop a chat, maybe we get that gentleman's or person's contact information. Happy to reach out after that for a little more in-depth conversation.
See another question here about it acts as a transfer switch. I believe that came in before we kind of went through those slides. So I hope those slides address it. If not, feel free to reiterate your question. Someone asked, can we get a copy of this great presentation? Thank you. We appreciate the compliment. Yes, I'm sure they'll be shared after we're concluded today. And I don't see any other questions in here.
All right. Well, thank you everyone for joining us today. We are right on time. I appreciate your attendance. You will be getting a link to the recording of this presentation.
The great recording, as they made it clear.
Oh, great recording. Excuse me. Yes, you'll be getting a link to the great recording shortly after. Thank you for attending. If you have any information, please feel free to reach out to Benny or Victor, or you could reach out to me and I could relay answers to them as well. We appreciate your time today and hope you have a great rest of the week.
Yeah.
Thank you, everyone.